Okay, this is Unit 15, Lesson 4. We're going to talk about area probability problems and construction uh, techniques on how you can circumscribe a triangle with a circle. In other words, how can I draw a triangle around a circle that only goes through the three vertices of the triangle? Okay, once again, let me remind you that if you think that you might possibly have any reason to write down a question, get yourself a piece of paper and a pencil or something that you can record it so that you can bring it to class so that you can ask it before we start any kind of work on this. Okay, so let's see what we've got with this. Okay, definitions and things. Areas can be used in the calculation of probabilities. Consider a circular spinner with 5 different colored sectors of equal area. The probability of the spinner pointing to the red is 1 over 5 because there's 5 sections and they're all equal, are 20%. Since 1 out of 5 of the total area is the desired area that's red upon which we wish the spinner to land. Okay, the general principle we will use in this lesson to find a probability where areas are involved is this. The probability is equal to the desired area of what you want to have for your outcome divided by the total area that's involved. Okay, these are some useful facts concerning probability. This is true in all probability problems, whether they deal with geometric areas or if there's just an algebraic computation. An impossible event has a probability of 0, which correlates to 0%. An event that is certain to happen has a probability of 1, which correlates to 100%. And the sum of the probabilities of all the possible events has to be 1 or 100%. If they do not, then there is some outcome that you have not taken into consideration. Okay, example 1. In a rainstorm, what is the probability that a raindrop that lands within this circle will also strike the shaded area if this figure is laid flat on the ground outside in the rain? Okay, notice what they've done here is they've told us what the major arc measure is, which is 303 degrees, and we have a sector indicated, so we're going to need to find that particular measurement, which will lead us to being able to find the area of that sector. Okay, so 360 minus 303 gives us 57 degrees for the sector. So to calculate what the probability is, we need the area of the sector divided by the area of the circle. So this gives us the probability is equal to 57 over 360 times pi r squared, which is all one term divided by pi r squared, which is going to reduce to 57 over 360 because the pi r squares cancel each other out. Okay? So once we have this, we calculate it out by dividing 57 by 360, which gives us 0.1583 repeating, which is approximately 15.83%. Okay, some more definitions. The Monte Carlo method uses random numbers as a statistical tool. Consider the case of a circle inscribed inside a square that's like we have shown here. If you pick random xy coordinates that you generate and place in the square, some of which also fall inside the circle, then by counting the total number of points that are generated and counting those points falling inside the circle and knowing the probability of a point falling inside the circle, an estimate of pi can be calculated. Okay. This is one of the ways that pi shows up in the real world. So what they're telling you here is pi ends up being a limit of what happens statistically in lots of things. Okay, example 2, they want us to calculate the probability of a random point within the square shown also falling inside the circle. Do this in terms of the symbol pi without using a numerical approximation. Okay, so we have a circle inscribed in a square. So what we're going to do is calculate that the area of the circle, which is pi r squared, which in this case is going to be pi times 2 squared, because 2 is the length of the radius. Because as you can see from the diagram here, the diameter is 4, so half of 4 is 2, so that's where the radius of 2 comes from. 2 squared then leads to the expression 4 pi. So that's the area of our circle. Okay, the area of the square, since each side of the square is 4 units long, is simply 4 times 4, which is abbreviated as 4 squared, equals 16. So the probability that something's going to fall in the circle when it falls within the square is going to be the area of the circle divided by the area of the square, which is going to give us 4 pi over 16, which reduces to pi over 4, which is approximately 0.7854, which corresponds to or correlates to 78.54%. Okay, example 3. The following map of a portion of a voting district was used in predicting the outcome of an election. The people living in the shaded portion, which is a semicircle of diameter 1 kilometer, are more likely to vote Democratic, while those in the unshaded portion are more likely to vote Republican. If voters are evenly distributed over both regions, what is the probability that a voter selected at random from this map will vote Republican? So, once again, we simply find the areas of the two parts that are involved and determine what the ratio is. Okay, so the area of this, of the unshaded part, the area of the unshaded, that's what US stands for, is equal to 2.25 times 0.8 minus 1/2 of pi times the radius of 0.5 squared. Okay, the way they got the 0.5 here is because they told us it was a semicircle with a diameter of 1 kilometer. So if you come down here, this distance from this edge of the arc to this edge of the arc is 1 kilometer. So half of 1 kilometer is 1/2 or 0.5. Okay, the other part here is simply the area of the rectangle, which is 0.8 times 2.25. Okay, so this gives us, when we calculate this in our calculator, it comes out to approximately 1.41. That's the unshaded area. Okay, the Republican part of this is going to be 0.8, or the region rather, the total region, not Republican, is equal to 0.8 times 2.25, which is the area of the whole rectangle, which is 1.8. Okay, so to find the probability that it's going to be a Republican vote is going to be the area of the unshaded, which is primarily Republican area, divided by the total area of the region, which is Republicans and Democrats together. So we have 1.41, which is the unshaded area, divided by the whole region, which is 1.8, gives us approximately 0.7818, which approximates or correlates to 78.18%. Okay, given any triangle, it is possible to circumscribe a circle about the triangle. The circle will pass through all 3 vertices of the triangle. Okay, think of the 3 sides of the triangle as being chords of a circle. Construct the perpendicular bisectors of any 2 of the triangle sides. Extend the bisectors until they intersect. This intersection point is the center of the circle. Okay, set the compass to the distance from this center point to any one of the vertices of the triangle. And with the point of the compass at the center point, draw the circle. Okay, so we're going to use construction techniques to circumscribe a circle about this triangle. So here's what we do. We got a triangle. First thing we do is we bisect each one of the side, or two of the sides. So we use the compass to find the midpoint of this and draw the line through it, which will be the perpendicular bisector. Do the same thing with another side and extend the line from that point straight out until they cross each other. So this points they got here marked C, very small up here, but it is a C. That is the center of our circle. If you take compass and draw and put the pencil on this point here while you hold it here at this center, draw the circle, it will go through all 3 points of all 3 vertices of the triangle. Okay, why does this technique of circumscribing a circle around a triangle always work? Okay, the reason why is the perpendicular bisector of the chord of a circle passes through the center of that circle. If you remember, we talked about this, that a radius touching the tangent line at the circle will be perpendicular to that, and it also goes through the center of the circle because it is a radius. Okay, so treat the sides of the triangle as chords of a circle. So the perpendicular bisectors of those chords must all pass through the center of the circle. Thus, the intersection point of these bisectors locates the center of the circumscribing circle. The radius of the circle is simply the distance from the center just found to the end point of any chord. So one of the vertices of the triangle is where that would be. And it's any one of those. All right, this concludes Unit 15, Lesson 4. If you have any questions, make sure you write them down. If you have any that occur to you before you get to class tomorrow, write those down. If you have something that occurs to you in class, ask that question also. Be glad to discuss it and to come to a conclusion before you're assigned any work from this. Thank you very much. See you in class.